Welcome to our webinar. We're going to be going over some CFD tools available on the market by Dassault. This is just a brief agenda. So we're going to talk a little bit about us. We're going to briefly look at the three portfolio of tools that we're going to look over. Then these are the three we're going to go over: FMK, XFlow, and Powerflow. And we're going to save all questions to the end. If you have any questions during the presentation, feel free to type them out just to save them there, and we'll go through those ones first. So a little bit about us. We are ENA2. We're an engineering consulting firm based out of Calgary, Alberta. We have roughly 13 employees, and we've been around since 2008, and we serve multiple different industries. Our services, as I mentioned, include engineering consulting, but we are also resellers for software, and Dassault is one of our channel partners. And for all the software you see, we are certified training center for it. So we can sell it, we can train you, and we can provide technical support. So as we're going to go into our fluids portfolio, I'm going to introduce our speaker. His name is Vishnu. He is our senior mechanical engineer here at ENA2. He has a master's in mechanical engineering and comes with us with extensive background in CFD. And he's going to walk you through our fluids portfolio. Vishnu?
Perfect. Thank you so much, Jen, for the introduction. So I'm going to start out by giving you a brief overview of the three solutions we have available in the Similia brand. Similia's focus has recently shifted to providing all possible solutions for virtually all of the 12 industries that we have available in the market today. And in support of that vision, for the CFD side, we have three major solutions available in the market. So we'll start out by talking a little bit about FMK, what we call as the fluid dynamics engineering role. So this role is very unique because FMK is the kind of a software or solver that a designer would be more interested in using. So anyone who is either a technical or a non-technical personnel can definitely use this tool. It's structured in a way where it keeps the user interface very intuitive and guides the user along the simulation setup process. And again, a killer feature when it comes to FMK is the strong connection that we have to the CAD geometry and the fact that it actually works on a platform solution. So everyone has access to a single source of data. People do not have to get confused in terms of revisions, and so it really helps in improving your engineering throughput or your engineering productivity. Moving on to the second solution we have available in the market, which is rather new in the Similia's fluids portfolio, is XFlow. And we'll talk a little bit more about how XFlow works in subsequent slides, but some of the winning points when it comes to XFlow is that it's very easy for you to model and very fast for you to learn XFlow. So literally users, when they start using XFlow, it'll probably take them for an hour, a little less than an hour to set up simulations. But however, with experience, they'll be able to actually set up those simulations, no matter how challenging they are, in nothing more than a few minutes. And then the third solution that we have available in the market, which is rather recent as well, is Powerflow. So one of the major features for Powerflow, and it has been an objective for this for the simulation software in itself, is to always try to capture real-world physics in a virtual platform. And the goal when it actually comes to Powerflow is by capturing this, they would like to reduce the amount of dependence that people are actually going to have on testing and prototyping, thereby significantly reducing their costs. All right, so let's start with FMK. Okay, so FMK is a very easy-to-use solution that's available on the platform, and it has the mentioned CAD embedded CFD. So if you do make any changes in the CAD, it automatically gets transferred downstream of the process in your simulation study setup as well. So if you look at the picture on the right top, you can see that when I do make a small change, when it comes to the geometry, that without any effort that is required by the user, you do see your boundary conditions for all you CFD experts out there, or your simulation study inputs accordingly changing, which is very cool. So this reduces the amount of errors that, say, for example, a non-expert could potentially commit, and really makes it very adaptable for designers and lets them perform simulations easily, effectively, and efficiently. And so in support of the fact that we use a platform, it lets you quickly iterate through designs, something in the order of 1,000. So it really helps you with figuring out a very good starting point for your product design, and it supports the early stage design development process. It's definitely very easy to use, and it's highly automated in the way that the solver in the way that the solution is structured. So we have automated body-fitted hexadominant meshes available. we have a guided user interface that kind of helps a non-expert to prepare the simulation the right way and gives them warnings and errors, and to be honest, makes sure that the simulation is prepared correctly even before submitting or running the simulation. So this gives confidence when he produces his results to experts or upper management in terms of his product design process. And it's also got some really new features added, which is high performance visualization. So we have now realistic rendering capabilities available in FMK as a result of the NRE, which is our new rendering engine that's available. FMK is a solver, is a solution that gives you access to not just one application, but multiple applications, which can be used for visualization, data post-processing. So you're looking at 2D and 3D streamlines, you're looking at vector plots, you're looking at contour plots, stuff like that can be very quickly prepared and presented to upper management. And finally, as an ending note, you can see that really awesome video where FMK is being implemented in the design of, I believe, a component that goes into the high-tech industry, and how he basically changes his mesh, how he basically evaluates his results, and really makes good use of the tool. Okay, moving on to the solver capabilities. FMK is definitely a competitive solver to the solvers that we have available in the market. So we do have turbulence modeling that's quite standard and effective. So we have our very well-known eddy viscosity-based turbulence models. We have our hybrid wall function approach that lets you prepare meshes computationally more efficient. And FMK is definitely very strong in addressing multi-physics simulation that's really picking up in the market today. So we have FSI, which is our fluid structure interaction, where a cool feature that we have in FMK is that it automatically can detect the interfaces between the solids and the fluids. And then the user in itself doesn't really have to go through any particular kind of a connection or a conformal mapping kind of process. We also have a CHD, conjugate heat transfer models, with supported radiation. That's also a little bit of a demand that we have in the market today. And as far as the physics coverage is considered, we have our very well-established RAMS, Reynolds Average Navier-Stokes solver, that FMK uses predominantly for steady state and mildly transient simulations. Its coverage is pretty standard for any CFD tool that we have in the market. So we have laminar turbulent flow modeling, compressible and incompressible flow modeling. But I think a winning point when it comes to FMK is that it also has the capability of modeling non-Newtonian flows, which is rather difficult and has a strong application when it comes to the medical devices industry. Okay, so we have a lot of applications for FMK for 12 industries in total, but I've just taken the liberty of just putting up some of the applications for the 3 of them. So we'll start out with the automotive industry, the transportation and mobility, basically. And here, the kind of simulations that we're looking for FMK to be very useful is we really want to be focusing on getting quick simulation results, but without compromising on accuracy. And so we don't really want to be spending a lot of time in preparing the geometry, preparing the mesh. So typical scenarios where we see, for example, would be equipments that go into the automotive system, like air induction or cold flow intake systems, where basically you're trying to understand the performance of the component. You're looking at pressure distribution, velocity distribution, and maybe thermal distribution. And then the same holds good when you're talking about exhaust manifolds and muffler systems. And since we did touch base upon the fact that FMK can work with non-Newtonian fluids, it has a strong application in the life sciences industry, where blood flow modeling can be done for organs and medical devices. And lastly, looking into the high-tech industry, because it's multi-physics in nature, we can address some really cool applications like electronic cooling. And if you are just interested in understanding, for example, a specific device's thermal or flow performance, and in an electronic equipment, as an example. Okay, so we're going to go into the next solution, which is XFlow. So XFlow is a very new and a very unique solution that we have available in the market. So it's based on a lattice-Boltzmann methodology, and it really helps in modeling simulations which are basically large eddy simulations, which is a little different than the traditional CFD models we have available in the market right now. But however, the true advantage that we have with XFlow is that it's very the large eddy simulations have been made in such a way that it's affordable. So if you are looking at several years back, LES, although was a concept that was available in the market, there wasn't any machine power to run these types of simulations, which we do have available, and also XFlow is one of the solutions that helps in addressing it. Because it works on a lattice Boltzmann methodology, I don't know how many of you on the phone are actually aware of the working of the lattice Boltzmann solution, but it's essentially particle-based. So we're not really looking at the simulation results from a macroscopic standpoint. So we are truly modeling the microscopic from a mesoscopic standpoint. And so since we are looking at the underlying solver, primarily working on the particles, we have an increase in fidelity than for example, the RAM solver has in the market. So when there's a need for performing simulations where fidelity is of the utmost importance, then you can definitely use XFlow for it. And when you come into the benefits of the tool in itself, we have minimal to actually almost no pre-processing effort involved, because it is, in a true sense, meshless. And what do we mean by that is that, you can directly have your CAD geometry imported. You can set up your simulation, solve the boundary conditions that is needed, but you don't need to go through a painful meshing process. Instead, what's really set up in XFlow is the resolution scheme. And once you do set up the resolution scheme, the grid or the lattice that works for this particular type of a solver is automatically generated after the simulations are submitted. So the user is not really spending any effort to address the generation of a mesh, and hence doesn't have to really worry about other aspects in terms of, like the quality, like the aspect ratio, the skewness and stuff like that. And because of the way that the solver's code is written, and because of the way that the product in itself is available to the end user, geometry complexity is not really a limiting factor when it comes to XFlow. So if you do have very complicated systems and even arbitrary motion for that matter, it can be very well captured in XFlow, and the user just sets up the simulation in a short amount of time. And then moving on to the ease with which geometries that can move in your simulations can be handled, it's very strong in XFlow. So we have two ways of handling moving geometry. So the first one is the rigid body dynamics with 6 degrees of freedom, which essentially means that you're trying to understand what would be the behavior of the rigid body when it is subjected to external forces from the fluid that it's exposed to. Or you can do an enforced rigid body behavior, which is where you actually give a specific trajectory or like a certain path to the body, or the body could be rotating or moving in a specified direction, and that can be directly enforced in a couple of clicks with XFlow. So maybe to better understand this, you can refer to the picture at the bottom right. So you see the wind turbine over there, and if I were to try to capture, say, the power that is going to be generated in the wind turbine as a result of the flow, as a result of the wind that it's going to encounter, we use the rigid body dynamics of those. It's just a click of a button where we activate it, and then we capture the rotation of the wind turbine with ease. And then you can translate that to something which is more quantitative, like the power generated. However, if you are looking at multiple wind turbines in a wind farm, for example, and you are looking at incoming wind, and you really want to understand what is the flow field around these wind turbines, or how is the flow field influenced between wind turbines that are close to each other. Stuff like that can definitely be done by knowing the rotation speed of the turbine blades, and you can do the enforced rigid body behavior. And again, one of the basic advantages we have for XFlow is that we do everything in the product in itself. So you're talking about flipping between tools to just set up a single simulation. So we do pre-processing, we solve it, and we also do the post-processing, which can help in generating highly rendered animations directly in XFlow. And it's one of those capabilities that is also GPU enabled. So it really helps in accelerating the speed of the simulations. Okay, and looking into the solver capabilities, we have adaptive refinement algorithms. So basically what we do is that we set up an initial resolution scheme, but you can also define criteria to carry out local refinement, which is automatically done by XFlow as the simulation proceeds in time. And the ways that we actually do it is that we basically have certain criteria that can help us in understanding and defining a wake in XFlow, and then you can correspondingly provide a resolution scheme for it. And if you are dealing with something like a free surface, or if you have a multi-phase application involved, then you can, again, set up your criteria for detecting the surface that separates the two faces. And again, XFlow will automatically resolve the interface very well. And as the simulation keeps explicitly moving in time, it's a time marching kind of a simulation, it will track the interface very well. We have a single consistent wall model that is used in XFlow for capturing the near wall behavior, and it's what we call as it basically uses a universal law of the wall. And it's a well-known methodology that has been used in XFlow because, and it's being used in other solvers in the market, to be honest, because we need to understand that as we keep going closer and closer to the wall or to a surface that's going to be a representation of a solid, we have to keep refining the meshes. But XFlow makes it in such a way that you don't really need to refine the mesh way too much that it becomes computationally expensive, and that's how the wall model kind of fits in. And when it comes to the large eddy simulation modeling, to be specific, the scheme is what we call as a WMLES. So it's called as the wall model large eddy simulation. So the way that it actually works is that it will compute the large eddies that is going to be generated in the simulation. And it uses a wall model for the near wall behavior or the behavior within the boundary layer. And when it is not able to compute, that is when the size of those vortices or those eddies are quite small, then because it becomes computationally challenging, we have our wall adapting local eddy viscosity models that's incorporated so that it keeps it affordable without compromising on accuracy. And multi-physics modeling can also be done very well in XFlow. So very challenging FSI simulations can be done. And also, if you want to look at, say, for example, the deformation of those rigid bodies, you have a chance to do that by coupling it up with Abacus. And if you look at the animation at the bottom, it's a really cool simulation that was done by one of Dassault's clients, Safran. So this is a check valve at a shutoff condition, which is virtually impossible for you to mesh or even try to simulate with the other commercial softwares out there with ease. But XFlow does a very good job of it and predicts the conditions where the check valve becomes highly unstable. And when it comes to industrial applications, we have a strong footprint in the marine and offshore industry. We have wave loading that can be very well captured on offshore platforms with XFlow that can help you in understanding the structural stability of those platforms. We have ship hull hydrodynamics, which can help in understanding the drag force development, and hence will help you in understanding ways in which you would be able to minimize the propulsion requirement for the ship hulls and basically save on fuel consumption. And if you look at the transportation and mobility industry, it definitely can be used for aerodynamic and aeroacoustic applications, which is standard again. But when it comes to lubrication, there are not many solvers available in the market that can do it very effectively and with ease. Lubrication is a very unique scenario if you want to do a test because it's extremely expensive. Because if you want to look, for example, the gear house that comprises of the gears that you want to test the lubrication performance on, it has to be made transparent, which is extremely cost ineffective, and that's just even looking without the costs that actually go into running a test study. So having an alternative solution that can capture something like lubrication with a very high level of accuracy is very important, and XFlow does a very good job of it. And lastly, in the energies, processes, and utilities industry, we have the hydropower modeling. You can extend to say that it can also take into consideration generation of, say, power from Archimedes screws or water wheels, in addition to what you see over there in this line. And you can also do wind turbine modeling, which we kind of touch base upon that. And last but not the least, I'm going to talk about Powerflow, which is the most recent solution that was added into Simulia's fluids portfolio. Okay, so with Powerflow, it's again a lattice-Boltzmann solver, but the key difference between XFlow and Powerflow is that it's been extremely validated in the industry. So it's been used more than 25 years. It is not a new solver, and automotive industries are very well appreciative of the level of fidelity that a lattice-Boltzmann solver like Powerflow can provide. So it was primarily used for ground transportation applications. We are seeing new applications developing with the use of this tool. It definitely addresses aerodynamics, aeroacoustics, thermal engineering, and water management types of simulations. And then when it comes to the geometry preparation, I know every CFD engineer has to go through a painful process of preparing the mesh. But the way that Powerflow actually addresses this is that geometry preparation is done very easily and effectively. You organize your geometries in a way that it will really save a lot of time in the downstream setup of your simulation. And when it comes to surface cleanup at the CAD level or at the mesh level, it's very well handled. We only do surface tessellation, or what we call as surface meshing, which can be done with just a couple of clicks on the mouse. And we have wrapping tools available again, which can really help in shortening the amount of time that the user invests in the preparation of meshes. And if you really want to just make a small change in the geometry, but you really are looking at what is the benefit you get from the simulation, we have mesh morphing capabilities available within the suite of products, and so you can quickly change your design at the mesh level in itself, and then just run the simulations for you to see what the kind of a benefit you're actually getting. And we have automated simulation preparation that is available through Powerflow's expert validated best practices. So if you set up the geometry and organize it the right way, which is most likely the case with experience, you'd see that when you import the geometry and you try to set up the simulation study, you only have a couple of clicks of buttons. You'd be able to set up your simulations in the order of minutes. And you'd only have to fine tune the input conditions or the boundary conditions, and that's just for verification purposes. And we have extremely good visualization, realistic visualization capabilities in Powerflow. So a testament to that would be a picture on the right that they used it for a VTOL vehicle. Standardized post-processing templates are also available that would shorten the amount of time the user invests in post-processing. And high-quality rendering and visualization actually comes in with the tool, which is very useful, for example, your marketing department if you are working on a product. We have availability again, in the standalone or in the on-cloud version, what we call as the Simulate Cloud, and that's very useful because you can directly fire up the simulation softwares in nothing but a single browser. You can share links of the sessions to other users who might want to work or who might want to evaluate. Maybe you might want to go through the stuff with your customer. It makes it very streamlined and very collaborative. And technical capabilities of Powerflow, it has very, very good turbulence modeling schematics. It very well predicts transient separation because the confidence in the tool pertains to have is to basically be competing enough to a testing scenario. It has automatic domain discretization, so the user doesn't spend too much time on meshing. And we have rotating and moving geometries very easily supported in Powerflow. So I'm not sure if you got a glimpse of that. It was in the animation at the bottom right. And you can do, it's been incorporated for threaded tire modeling. Inlet turbulence modeling is a differentiator than other tools that we have in the market, which can bring it a step closer to fidelity and really help in modeling those real-world scenarios. And velocity freeze is very good with Powerflow, and it makes the simulation more computationally efficient. Long story short, you'd find that certain disturbances within a CFD simulation not really evolve in time, no matter how long your simulation duration is. So Powerflow automatically detects these particular regions, increases the velocity, and uses the computational resources when things are rapidly developing, where you need to be predicting certain separations, certain features with a higher level of accuracy in a shorter amount of time. Acoustics modeling is very good in Powerflow, so we can actually understand the noise that is generated from flow. Literally, you can virtually capture the noise as if you were sitting in a car and trying to understand what the noise would be when you start the car's HVAC system. So that's a generated MP3 file, and you can get a clear difference of what the observer is going to hear. And lastly, if you look at the flow-induced noise detection, acoustic simulations are very challenging to perform, not just to run them, but to also figure out what has actually caused the noise. And we have a patented application that's available in Powerflow that can order the rank sources based on certain geometries or geometry features and really help you in structuring your optimization process with ease. Thermal modeling is also supported in Powerflow, where you can do battery thermal modeling. And if you want to look into human comfort and understand what the effect of the human is actually going to be for, like a closed space, like in a car, for example, we have human comfort models available, like the very famous Berkeley human comfort model. And lastly, looking at the industrial applications, we have car and truck aerodynamics, where people don't even really rely on physical prototyping and testing anymore. They are very confident in terms of the results that we get from the simulations. We have HVAC noise that is that can be captured with Powerflow as well when it comes to the automotive industry. Equipment noise, where predominantly the noise comes out from the inlet or the outlet portions, or if you have any particular kind of a fan running within the system for cooling applications, which is typical for industrial equipment systems. Equipment noise can be very well estimated. You can understand the radiated power, get the near field and the far field acoustics. And for the aerospace and defense, again, Powerflow has been significantly used to predict the drag and lift performance when it comes to an aircraft. And if you do have jet noise modeling involved, where you want to look at the noise that's actually going to be generated from, say, the jet engines, you have a chance of doing that very well in Powerflow. All right, and then summarizing what we went through today, just for the key takeaways. All right, so we have FMK that we talked about a little bit. So the winning features is the fact that it's CAN enabled. It's very easy for a non-technical expert to use. We have automation involved in the meshing and in the fluid extraction process. We have the RANS code, which is basically industry competitive. When it comes to XFlow, it's meshless, so it's a very good simulation software to look into when you really want to be saving on simulation time, when you want to model challenging simulations. It works on the lattice Boltzmann solver, the LBM solver that we talked about. It's excellent for modeling moving bodies, multi-phase, and free-surface simulations. And fidelity is guaranteed with XFlow because of the LBM solver, and it's inherently transient. And finally, for Powerflow, it's a solver that has been focused on the ground transportation applications. A couple of things that we talked about before, like the air acoustics, thermal engineering, soiling simulations, and we have best practices that can help you in modeling it the right way. And we have high fidelity and inherently transient types of modeling schemes. And on that note, I'd like to conclude the presentation and open the floor for any questions.
So guys, we're just going to hang around for a bit. Feel free to type out your questions or unmute yourself to ask anything, and we're happy to answer any questions you have.
Hi, thanks for the presentation. It was quite clear and it's very interesting. I'm like more working for like two-phase flows. So I have seen like your slide, and especially for the like lattice Boltzmann solvers, I'm quite interested in. And just to pop up the question, like I see, like I have seen like on slide 12, you have an example. No, you have mentioned that. No, it was slide 13. Sorry. You have shown a picture that is on wave loading. So if I understand correctly, like the XFlow solver, it can solve the two-phase flow with a free surface, correct?
I'm sorry. Hi. Can you repeat the question? I think we were on mute, so we couldn't hear your question. Can you repeat it if you don't mind?
Yeah. Right. Can you hear me now?
Yeah, I can hear you.
Yeah. So my question is like I'm more like working on like a two-phase flow for now, and
Okay.
like I have seen like on your slide 13, you have shown a picture on the wave loading. So basically, if I understand 13, yeah.
We're just going to the slide. Yeah.
Yeah. So I have seen like this picture on the left-hand side. You have shown like a wave loading. So if I understand correctly, the XFlow solver, it can solve a two-phase flow with a free surface, correct?
Yes, it can do free surface modeling. That's correct.
And that is also like related to another question. I have like worked with Powerflow at a certain point before. Just to know, just want to know, like, does Powerflow like offer also like a two-phase flow, like multiple like flow, multiple phase like solver, for the current version, or it's still like a single phase flow?
It's a yes and a no answer that I can give you at this point, but I can definitely give you more information. You're right. Powerflow has been predominantly focused on single-phase flows, but we have applications where water modeling has been involved, and to my understanding, we also have snow modeling that is involved as well. Typical applications we're looking at is, for example, soiling effects that can happen in the windshield of a car or in the sensors of electric vehicles. Or,
okay.
Yeah, or snow modeling. That's something that we have recently started looking at, because It is right. We are seeing a lot of traction with multi-phase applications these days. And so Powerflow is able to address the snow, and I want to say ice, but I have to double check on that. Yes, but it can definitely address snow and water modeling at this point.
Right. So basically, it seems like the XFlow is like you have like I mean, this solver has solved like the multi-phase flow problems like kind of like earlier than Powerflow, right?
Yes, because the foundation, the way that XFlow is built, right from the solver and the product level, is completely different. And you come from a Powerflow background, so I'm pretty sure you understand that it comes with a completely different approach, and there is no mesh involved. So the way that the solver and the product is built, it's easy to address multi-phase applications. So this could extend to even oil and water types of.
Because we are like more like interested in like some like free surface like in between two kind of like materials, and then like the cavitation problem inside it. So it's good to know. And my second question, and perhaps the last one, is like on slide 12, just the slide before, also on this XFlow solver. You mentioned that in this solver you have like a single consistent wall model to tackle like adverse pressure gradients. Actually, like I'd like to know a little bit more, like how you you tackle like the adverse pressure gradients. Because like to my from my understanding, I think this is a quite tricky problem. And I myself, like I have have dealt with that like during my PhD before. So I thought like if we have something that is comparable with some sort of validations, etc., already for this solver, and it's validated, it would be a good news to for some kind of like industrial use. Could you explain to me or show me a little more on that side?
Yeah, I can definitely share more information in terms of how it's validated in the industry. To add more to the wall model, it's a little bit. I mean, to be honest, I don't have all of the information on how the wall model, the exact schematics of the wall modeling is done in XFlow. It's a little bit modified than traditional wall models we do have available, but I can definitely share more validation studies for you if that can get you to understand maybe the accuracy and the effectiveness of the wall modeling scheme.
Because actually this is a point that is quite interesting, because I have compared like before some direct numerical simulation using Navier-Stokes solver with lattice Boltzmann, but with Powerflow. But I have never used XFlow before. So so I think if this is like already like has been validated against some kind of like reference cases, it would be a quite like impressive progress on the LBM like lattice Boltzmann based solvers.
Sorry, and maybe just to add to that point, like, are you looking at any specific application for accuracy? Like, what application are you?
Oh, well, it's just like like this code, for instance, like for the validation against, I don't know, like some like velocity profiles or some sort of beta C or something like that, to a reference case. I mean, to already see like whether this wall model works properly. Because I mean, I have never used XFlow. It's just like when I saw this like features, I consider it like very promising. But it's just like I need some more information on that side. Especially the adverse pressure gradient is quite a tricky problem. Especially on some kind of like blade surfaces, etc., because it's we can have like a quite large or very high adverse pressure gradients, yet the flow still stays attached. So sometimes it's very tricky to.
It's tricky, yes, and this is the turning point when it comes to aerodynamic simulations too. That's where the accuracy comes into question. And so, definitely, I'll definitely send over some validation studies where that problem is critically addressed. But maybe just to add to that, Yes, it has been applied for aerodynamics, and I can tell confidently it's also been applied for air acoustic problems as well in the industry. So I will collect more information and share it with you as validation case studies.
Yeah, it would be very helpful, like I mean, the first is like the two-phase flow information, like some sort of examples, etc. But you have a kind of like show that from picture. And secondly is like the how they tackle or validate the model like that is on adverse pressure gradients. If you can offer that kind of information, that would be very helpful for me.
Oh yeah, absolutely.
Yeah. That's it from my side. Thanks. It's a very clear the presentation. I appreciate that.
No worries. Thank you so much.
Thank you for your question. Anyone else?
Okay.
It's Powerflow feasible for large.
Oh, I just got to. Sorry, guys. We're
1 second. Let us just get that chat open.
Into the chat. There you go.
Okay, so the question is the Powerflow more feasible for large-scale flow separation, such as aircraft in condition of deep stall, than other CFD tools in terms of accuracy?
I would say stalling conditions are better addressed with XFlow than Powerflow, because I think it's important to understand between Powerflow and XFlow, both of them are lattice Boltzmann solvers. But when it comes to maneuvering, when it comes to stability conditions for aircrafts, I've seen cases where they've done Cobra maneuvers. I've seen cases where people have tried to predict landing scenarios on the aircraft that sits on the ships. And so I would actually address the solution for this to be XFlow. So that's one part of the question. Such as aircraft in condition for deep stall, and other tools in terms of accuracy. I'm not quite sure if I can confidently say that this is more computationally efficient than other tools, because we really don't know what the other tools are at this point. And to be honest, if you are looking at it a Navier-Stokes approach with an FVM, like a finite volume method, then it's going to have a different way of addressing the problem. So I believe XFlow, first of all, would be a better solution for this. And if you are comparing the Navier-Stokes and if you are comparing XFlow and Powerflow, because of the way it's modeled at the mesoscopic level, accuracy should be technically higher for XFlow or Powerflow than the other Navier-Stokes solvers you have in the market. Because Navier-Stokes works more on the macroscopic standpoint. XFlow and Powerflow really work on the mesoscopic standpoint, where we literally track the particle distribution.
Hope that answers your question a bit better. If you have any follow-up questions, just let us know. No problem. Okay, does anyone else have any other questions for us? Okay, well, if no one else has any other questions, we just want to say thank you again, guys, for joining us. We hope this was informative. Feel free to reach out to us with any other questions you have after the fact. We're going to be sending out a recording of the webinar as well, so stay tuned in your inbox for that. And with that, thank you so much, and have a great day.
Have a good one, guys. Take care.
Thank you.